Okay, welcome back, everybody. Welcome to the 5th lecture of Intelligent Systems. And amazingly, I think this is always for me also the beauty of the period 5 is that it's so condensed. It really that we're already about a quarter through the course and a third through all the material that you're going to see after 1 week of lectures. So I think it's quite interesting always to see this. As we are progressing so fast, I think it's also important that we get feedback very quickly, very early. So I just want a quick round of feedback, whether you think things are going in the right direction or whether there's anything we could adapt. So how did the working groups go on Friday? So did you go to the working groups and did you get the help that you needed to understand the theoretical material? Is there anything I could discuss with the TAs that they should do differently or better? Yeah.
In one of the questions, I don't remember which one exactly, but it was very, the question was phrased along like with min and max algorithm. And so if you had the graph, you had min, max, min, I think.
Yeah.
But it wasn't, it was actually wrong where it wasn't clear where min was making the decision and max was making the decision.
Okay, so yeah, so it's I'll look at the questions, but did the TA did you sort it out during the TA session?
Yeah, there was TA.
Okay, good. Because I didn't get the feedback back from was it Casper? Oh, you don't know the name. The one there will be some extra exercise. He thought of some extra exercise that he wanted to distribute to make things more clear as well with the alphabet pruning. So it's always easy to do this confusion. And should this happen in the exam, that we make such a mistake and it's unclear, then it's a digital exam, but we can always fix it afterwards. So in the marking. So if you say, okay, but I gave this answer because it was unclear whether min or max should start, then we just fix it afterwards, and you will get the point anyway for both possible interpretations of the question. So I apologize. This will always happen, that there will be questions which are ambiguous, but we try to minimize it, of course. Yeah.
We had this discussion when we were like using basic calculators like
yeah.
Whether we should include the goal state or not in the answer.
Sorry, the root.
Goal state.
Yes.
So it's like equals G. So should we add in the because my answer was after we copy, then we find the goal. So maybe we have to add it.
So this is more sort of an accountancy problem. So how do we make sure that when we ask these questions in the exam, that the question and the answers are unambiguous? So in the exam, we will try to formulate explicitly what how the counting works. I think in the traditionally find the root is the level number 0, but you also find people counting from the root. So there's no good answer here. What I can promise is that we try to make it as unambiguous as possible. And if you have the feeling afterwards that in the exam we did it incorrectly, or you had a reasonable interpretation of the question, then we can discuss it afterwards and you will get the points for the question. This is sort of very difficult to make an analysis. Yeah.
Maybe in the more text data types, so the error messages are a bit more descriptive than the native Python.
Okay, so that's a very good suggestion. Would you mind posting this on Piazza for the PAs who work with the code? Because I can give this also through to them, but they will read it immediately when you put it on Piazza. And I think they have been quite good at reacting pretty quickly at the questions that came at Piazza. So I really recommend you to write all the questions you have on Piazza and not personally to me or to to Michael or so. Post them on Piazza and we try to answer as quickly as possible. And that is also a good suggestion. I'm not sure whether we're going to fix it in this edition, because then if you make a poll, you might become difficult for some people. If we have a new version of the code base, so it might be more secure to leave it. But it's a good suggestion, definitely for the future. Okay, so what I hear are that there are some sort of smaller things that we can adjust, but in principle, we were quite happy with the way the Friday was run. Did you have enough computer support in the labs? Were there sufficiently many TAs to help you when you had questions, or did you have to wait for a long time before you could get the help that you needed? No? So that also worked fine. Also, the group sizes were okay in the labs, yeah? Okay. So the videos, as I said, it takes me about a couple of hours of time where I really have to be around to do the rendering. And that's a difficult time to find. So it might be that it takes me a couple or even more working days before I can publish the videos. So that might unfortunately take a bit longer. But for the rest, all the materials should be available now. And I posted an announcement for frequently asked questions about the milestone and about the resits this morning. So please check those first before you ask questions about these topics. Okay, so then I think we can move on. And move on to the second type of topic about intelligent systems, and that is the logical agents. So that's agents that base their decisions on some kind of logical, formal reasoning. Yeah? And for most of you, this is particularly what I'm going to talk about today is repetition. It's repeating the things that you have seen in logic and sets, and partially also in knowledge and data. So it's just the basics of some formal systems and logic theory, but now from the perspective of the games or the decision-making in complex systems for logical agents. And I want to do that starting from the motivation of the Schnapsen game, where we have, remember the first phase of the game where we have all those many different ways in which the cards could be distributed. So the uncertainty about the cards that our opponent has, the unobservability of the environment, as you want to say. And the one way, I mentioned that very briefly at the very end last week, to implement this game is what the algorithm RDeep does. And that is basically guessing one of the belief states, which means fixing one of the cards, the possible card combination that it has, and just running a game and checking who won, and do that very often. And then you just average over whether you win or lose. More formally seen, this is called perfect information Monte Carlo sampling. So it's perfect information means you turn the imperfect information into perfect information by just assuming one possible distribution of the cards, so choosing one of the belief states in formal terms, and then making a rollout, just have the player play, and actually you have them play randomly against each other, just following some random choice of cards. And then the decision that you make for this specific state that you're in is just made of the basis that a random game over a randomly chosen belief state wins or not, and you play hundreds or thousands of games, and you just have the majority and you follow the majority. Yeah.
I think the full depth of 8 doesn't quite finish the game.
Yeah, so the RDeep is limited to 8, I think, and you could, I think that there are more clever way of doing this, and this could be something that you, for example, would like to do for the final project. So you could say, I do a full rollout over all the full game, and you, for example, you stop at phase 2, and then you do an alphabetical pruned minimax. So there are different variants of it, but so the RDeep is a variant of the perfect information Monte Carlo sampling, just by taking some random belief set or a sample of belief sets and doing some random rollouts and averaging over how good it performs or not. Yeah.
Does that take us 8 rounds or 4 rounds?
I don't know the details of the RD. Sorry, I think it was 8. No, I don't even know. So I knew last year, but it's just the principle is the same. And there are details on all different choices that you can make in order to implement it. But the idea is always the same. You choose a random sample of belief states, so possible card distributions, and then you have your machine play, and you average over who wins and loses, and you take the decision of the one that wins more often. Yeah. So that's the principle of the random sampling algorithm, and it works terrifyingly good as opposed to all other methods. So this is the one that you will measure yourself against in the final report that you write, in the research that you do. So from a human perspective, this method is so stupid, or I'm very uncomfortable with it that this wins, because this is not how we would do it if we play. So who's now played some more games of Schnapsen? So can I have a raise of hand? So who of you has really tried to learn the rules a bit and play it a bit? Okay, so that's the majority. That's good. So who would consider themselves now really almost quite good at the game? Yeah. Okay, so some of you. So look at this situation. Yeah, so this is your deck of cards. And we are in phase 1. We know that spade is trump card, and your opponent plays the queen of, what is it? Diamonds, yes. So which of the cards would you play?
King of diamonds.
King of diamonds. You would play the king of diamonds. Why would you play the king of diamonds?
Because king is not that high value. If it was ace of diamonds, then I'll probably draw.
Okay. So describe a strategy that you would apply here. Okay. So there is no marriage that could be made. What else? So you basically say you want to gain the trick, yeah? Because otherwise you're going to play this one as well. It's the same. So you play the king of the same color because then you gain the trick. You also have a suggestion?
Yeah. If you play the trump suit now, instead of some other time, you gain a relatively small amount of points by using the trump suit, which you can also use the name point to get more points.
Okay, so you might not have understood that, but there would also have been the opportunity to gain the trick by playing the trump card, but you don't gain that much, and you can still, it's safer. I mean, you didn't say it, but I think it's also useful to keep your trump cards to the second phase, because this is where you really make the points with the trump card. So here's quite a lot of knowledge about the game that we discussed here that makes a decision, that suggests that we should take this card. So let's summarize. So I think it's good to make the points in the early stage. It's good to not play a queen or a king if it's still possible to make a marriage. I think that was also mentioned. But here it's good to play it because we can't make a marriage anymore. We could also gain the trick with the trump card, but first there is no need for doing it. And secondly, we're still in phase number 1, so it's good to keep the trump cards. So there is a lot of human knowledge, qualitative knowledge, in this situation of the game that we have as humans, but yeah, so it's not taken into account at all when we talk about the Monte Carlo, the random sampling with perfect information Monte Carlo sampling. So now the question is, can we somehow model this human knowledge in knowledge bases so that it becomes useful for games? Yeah. So that is basically the motivation for what we want to do now. There is, of course, a different way of doing that, and we've already seen that, and that is via some heuristics. And that heuristics would, for example, say if you have a higher value state, the next state, the one after you play the card, has a higher state if you still have trumps on your. That could be one. You count the number of trump cards, and the more trump cards you have, the better your future state. Yeah, so I think that could be a good heuristic. Another heuristic could be how many points do you gain? And then you would say, okay, 7 points is not that much, but at least I keep my trumps on the deck. You could also have the heuristics of how many potential weddings do I still have on my hand. And if you know that there is the queen out here, then you know that this will never become a potential wedding. So there's some way of modeling this in heuristics as well. But it becomes quite complicated, and it becomes, I have to translate all of this into some kind of numeric value. And the question is whether it also makes sense to model this kind of knowledge in an explicit declarative way. And to answer this question, I mean, this would be an interesting research question for your project in the last week. We first need to understand and look at ways of modeling this in some logical formalisms. And that's what these 2 lectures, 3 lectures will be about. And as you've all seen the modeling side, I also want to particularly get into the reasoning side, so the automatic reasoning side of logic. So how can we automate really these reasoning processes on a machine and in an algorithmic way? So that's the plan for tomorrow and on Wednesday. So we've seen that, and basically you have in your game, you have 5 different options, and then for each of those 5 options, you play any of your 5 cards, you can now evaluate whether they belong to a certain state that has certain properties of a state. So your choice could, for example, be one where you adhere to the criterion of smallest card first. So you always play the smallest card. Then you need to model what is a small card. So the jacks are smaller than the queen, and the queen is smaller than the king, and so forth. Yeah. And this is the kind of things that we now try to model in some language, and to keep things simple, we also will keep a relatively simple language. But obviously, in later stages, if you like this and if you want to do research in this field, then you will see that there are many, many different formalisms in which you can model these kind of information as well. So what's a logic? Just to go back, I mean, you have had a course about it, so I will give you also my personal view on what's a logic. The AI students have heard quite a lot of that in the knowledge and data course, but for the others it's a reminder, or for some of you it's even, I think, new material, so it should, for those who have never seen this, try to read the reader. There is an explanation for that. So this is really useful if you have imperfect information and you have knowledge about the environments and about the rules of the games, for example, and you want to explicitly reason over those in order to derive facts that are implicitly modeled but not explicit in your data. Yeah. So what we really try to do here is to make implicit knowledge about games that we can model formally, to make those explicitly available for a game engine, for example. And in the book, this is explained with the idea of a game that's called the Wumpus World. And I have to show this because I think it's really nice. I hope it works. And it's a visualization that one of your colleagues has done, I think, a year ago, just for fun, with a virtual environment. What is it? Virtual reality environment. And it just shows how nice, how easy it is to make something. See how this works, and to imagine how you could use this very simple game as a basis of some kind of decision making. What you see here is someone who explores the Wumpus World, and there are different dangers that you can face. You can fall in a pit. And what you see here is the space, the search space that is built during evaluation of this world. So the more steps he goes, the more he recognizes what's happening in the world, and you can face the Wumpus, which is the monster. You don't want to see, you can fall into a pit, so you have to sense, smell, and and by this exploratory search, he basically walks through these different rooms. And all that's underlying this logic of this game, of this VR game, is this very simple Wumpus game that we're going to see in a minute. And basically, I think it's always some smelling that's happening. Here's some smelling, and when there's a breeze, when you sense a breeze, then you know that there must be a pit next to it. And if you smell something, you know the Wumpus must be there. So you have to do some reasoning over how safe is a state and whether I can go there before I'm hit by a monster or a warrior or whatever. Yeah. And at the very end of the game, you then find a pot which glitters, and as you can sense the glitter, you know that there must be the treasure must be there, and you find the treasure in the end. Yeah. And of course, this is not about the visualization, but just the idea that there is some kind of game logic underlying such a VR. And the game logic is very similar to what we are going to look into here now. And that's the Wumpus World. It's an online exploration game, like you saw. You always are in one state in your world, in a room, in a maze. You do not know what's in the next room, but you can sense some things. You can breathe, as I said. You can smell, and you can smell a monster, or you can feel a breeze if there is a pit around. This is an exploration game. We have explicit statements, so it's we know exactly if we move to one room where we end up. So it's deterministic. There's no changes. We'll see in a minute what the properties of the game are. But these logical games, these logical agents, can also be used in other domains, in other games, such as card games or board games. We use the logical reasoning to determine the next state in which we want to go. So we'll see how to model this Wumpus World example in a state space, and then what kind of decisions we can make based on logical reasoning. And the idea is that the logical agent represents some states and the actions, and what it can do now, if it perceives new things, then it can sort of reason over the information about the games and the state itself that it has perceived in order to come to a decision. And basically what it does is that it deduces hidden properties of the world, and it then deduces the appropriate action based on these properties that it has derived. Yeah? So here's a simplified representation of a state of the Wumpus World. And basically, here is our warrior. You start here in 1-1, and this is all the information that you get if you have the perfect information about the game. And that basically is that there is a stench next to the Wumpus. The Wumpus is our monster, and in all the adjacent fields of the Wumpus is a stench. We have the pits, and in all the adjacent fields of a pit there is a breeze, and there is the treasure is here, and if you have the treasure, there's also the glitter so that you can see it. Okay, so this is the state, but it's an exploratory game. So when you enter this game in this field 1-1, you do not know anything. So you start from zero information game, and you build the information when you move around. Yeah. So just let's get back to the first lecture. So what is the kind of environment that we're dealing with? We have some performance measures. So you want to collect points, for example, or you want to move as quickly as possible. So you want to have a cost for each step to each room, or if you fight, you want penalties to using an arrow, and so forth. The environment is sort of, this is the definition of the environment, whereas adjacent to Wumpus are smelly, adjacent to pits are breezy, as I said before. So this is the set of the rules. You can kill the Wumpus, and at the end you go to see the gold in the same square. So let me switch on the light again. This is better, isn't it? Yeah, so you can still read it, yeah. And then the sensoric information that you have in this exploration game is the breeze, the glitter, and the smell. And the action that you can take is move left, right, up, and down, to grab the gold, to release the gold, to shoot an arrow, and so forth. And we will look at the very small subset of this, but of course you can think of really extending this to make the environment far more interesting. So it's not observable because we don't know the state in the beginning. So we only have local percepts, and we can have to sort of reason over those percepts that we have and the rules of the game that we know in order to make the decision for the next step. It's deterministic because I've shown you the state in which we're in, and as soon as the person makes a move, it just moves to the next state. But it's clear that whenever it makes a decision in which state it ends up with, it's static, nothing happens, the Wumpus is not moving, it's discrete because there are only a very small and finite number of steps per state that can be taken by the player, and it's a single agent as the Wumpus only sort of tells us part of the environment. But you could easily think of how to extend that to environments where, for example, also the Wumpus moves or these kind of things, which would make the game far more complicated. And this is what's called an online search, an exploratory search. So you're in an environment in which you move through the environment, and your percepts change whenever you move. So let's see how this works out. So remember the situation that I showed you is that here is a pit, here is a pit, here is the Wumpus, and here is the gold, and we start in this corner. So what you basically do is that you have a knowledge base in which you model the things that you know about the environment. And the things that you can perceive are a smell and a breathe and so forth. And basically the first percept that you have is that you can't smell anything, and you can see, can't feel a breeze. So you have no percepts, and that basically means that you can move freely to the right and to the top, because you know that there is no pit and there is no Wumpus. Yeah. So based on this very simple perception, you can have a very simple. You don't need to reason. So here, because we know there is no, as I said, these two states are okay. So then you move to the state 2-1. Yeah. And now we have we feel a breeze. Yeah. So basically, in this stage, we feel a breeze. Yeah. So our agent A is in 2.1, and it recognizes that there is a breeze. What does it mean? It means that, yeah, sorry? There's a pit and an adjacent cell, exactly. So there's a pit here, that's why we have the P question mark here, or there's a pit here. So what should the agent do? It can, of course, it could take the risk and say, I choose one of them, it's a 50-50 chance, and then I die. But it could also say, oh yeah, but I also know that in 1-1, it's a safe place. So I can also go back. Yeah? So if you go back, then the other option is there is another safe place, namely the one above. So if you go to 1-2, there's the agent now, you feel that there is a stench. What does it tell us? The Wumpus is in an adjacent field. Yeah? So now we know that either the Wumpus is here, or it is here, or it is here. Yeah? So the Wumpus is in 1.3, or it's in 2.2.
Reason that it's 3-1. So
of 1. It's 1, 3, so it's Wumpus.
In 3, 1?
Yes. The text says 1, 3.
Yes, the pit is in 1, 3.
Doesn't show the feet. That's Wumpus.
Oh, yes, the Wumpus should be, that should say Wumpus. That's what I think it should say. So, we know that the Wumpus is not in 1, 1, because we've been there, yeah? We also know that it's not in 2, 2. Why do we know that it's not in 2, 2? It says it there, don't look, but why is it not in 2, 2? Yeah?
Wumpus cannot be in a field.
If the Wumpus had been here, we would have had a stench here. Yeah, so that's basically the explanation. So if the Wumpus had been in 2, 2, a stench would have been recognized in 2, 1. So the Wumpus is in 1, 3. So that is correct here. Yeah? Then we know that 2, 2 is a safe place, because there is a stench here, and the Wumpus is here, and there is no Wumpus here. So this is a safe state. But then we also know that this is a safe state, that there must be a pit here. So it is correct what is written there. Yeah? So this is a safe space, safe state. And because we had the breeze here, we knew that there was being a pit in an adjacent field for 2.1. And if, as it is not here, we know that it must be here. So what's written there is correct. Sorry, I was doubting myself. So the decision that you can make on the basis of this reasoning is that the Wumpus must be here. There is no pit here, so I can move my agent A from here to here. Yeah? And then I know that this is a pit. What do I have in terms of new sensoric information in 2, 2? Nothing. So I can now reason that I can now move here or here. If I move to 2, 3, then I detect the glitter and I won the game. Yeah. And you could probably, because this should also be safe, you should go there. You realize that there is a breeze, so you should go back. There might be one intermediate step before you can do the safe decision. But what this all comes down is that you make some kind of reasoning on which are the safe states. And the safe states are always those that are not adjacent to one where you have a stench or a breeze. Yeah. And of course, this is now what you want to model in a game in some formal way, so that the algorithm do the work for you, while we can now model all this information in some kind of formally correct way. So basically what we do is we develop a knowledge base, and this knowledge base has all the rules of the game, plus the observations that we have. And then what we want to show is, when we have to remember the decision, where should we go here in 2.1? Should we go there or should we go there? And the decision is basically that when we are here, we know that it's a safe place, and we show that by what's called model checking. So that's some logical reasoning based on the information that we have from the knowledge base, and so that's the gains and the observations. And we can do that for all the fields in the game, all the squares in the game, by just checking whether there is whether we can reason that there is no pit and no Wumpus in these squares. Yeah. And in the next steps, we're now going to look into how we can formalize this, so that we can just use simple logical reasoning to help us decide on whether it's safe to go to one of the rooms or not. And we're going to do that with logic. And I briefly want to spend a couple of minutes before we have the break on what is a logic for me. And a logic to me has 3 elements. So it's a formal language in which we have a limited set of sentences that we can write down, and they have some kind of intended meaning. But it's important that we have a formal way of writing down all the legal sentences of my language. And this is defined by the syntax of the language. Then we have a semantics of the language where we assign a value according to the intended meaning of those sentences to each of the sentences. And then at the end, we have a calculus. We have a machine that helps us determine whether a sentence in the language, what the intended meaning of this sentence in the language is. Yeah, so it's always these three elements: is the syntax of the language, the semantics, and the meaning of the language, and the algorithms that you have and that you can implement on the machine. And we are mostly looking at the semantics of the languages today, and on the calculi tomorrow and on Wednesday, because this is sort of the intelligent systems AI side of how can we implement this in an efficient and effective way that we can really make the decisions based on the logic of the games without us having to do all the calculations, but have the algorithms do this. So what you need is the syntax, which are the legal, the well-formed languages, expressions of the language. Semantics, what do these legal expressions mean? And we will use a model theoretic semantics for that, as I call it, as it's called, not I, but everybody calls it like that. And then in the end, how can we determine algorithmically the meaning for these legal expressions? And you all know, I mean, most of you have seen this in the previous courses, but you also have seen it in school, where you have the arithmetic as an example of a formal system, and there you can make the distinction between legal inequations, and basically you know that something like x plus 2, so on the one side we have a term that has a variable and an operator and numbers, combined with an operator like bigger than or equal, and on the other side another term like a variable y is a valid term in arithmetic. Even though we don't know what it means, we all know this is a good way of writing down an equation. While if you have something like x2 without an operator between the two and a plus y, it's not an equation because it doesn't compare to terms. It's not even a term because this thing is undefined. So we need some unambiguous way of defining the legal terms in my language. Because if I give a computer program now any of those terms as strings and they should now do something with that, they should calculate, they can't because they can't even determine what they are supposed to stand for, those legal formulas. And then we assign some meaning to those inequations in mathematics and arithmetic. So for example, if we have the inequation above, then we know that it's true if we choose a certain value for x and if we choose a certain value for y. So if you choose x to be 7 and y to be 1, then this formula certainly becomes true. If we have another inequation, such as this one, x plus 2 is smaller than x plus 3, and we know that we look into possible worlds of natural numbers, then we know that it's true for any choice of variable value x. So whatever I choose for x, this will always be true, this inequation. And I also know that in a certain world, one of them could be false. And then we have different ways of calculating with this. You've learned that algebra in school, where you take a complicated equation or inequation and you transform it in a way so that you can prove, for example, that this one will always be true. Because if you deduce x and you will show that 2 is smaller than 3, in the middle one, this one in the middle, this will show you algebraically that this is always true. So that is a bit of calculus which we've learned at school. And there are different examples. So I think one in which you're dealing with every day as well is programming languages. You know this code, you can look at this code in Python, and does anybody see what it does? Sorry? What does it say?
Factorial.
Yeah, the factorial it does. Yeah. So it calculates. It's a factorial of 23 calculated here. So it starts with 23. It starts here with 23 times plus 1. So until it gets to 23, it multiplies the values, increasing by 1. Yeah. So this is one way of writing down a program for factorial of a number n. Here is different syntax for the same thing. Yeah. So and this is not for 23, but it's a general idea for the function in a different pseudocode language, which is exactly the same thing program, but in a completely different way. So we use different operators, we use semicolons, and so forth. So here you see that you can write the same thing in different ways, and your machine needs to interpret this. Yeah. So you need an interpreter for these, or a compiler for these different syntaxes that calculate the same thing. But then you have also some kind of mathematical object, and that's the mathematical function of computing factorials, which is the intended semantics of your program. There is more meaning that you can give to this, and that is the sort of the formal semantics. We can now write it down really as a mathematical function that we define. And in the end, we even have some kind of procedural semantics, namely what happens within the interpreter and the compiler, and really comes out at the end. And of course, when you design a formal system, you want to be sure that you have a compiler or an interpreter that knows what this means. So if you apply the Python interpreter on this code, it would just tell you, I have no idea what you're talking about. So you want the syntax to be understood by your program, and then you want to have an intended semantics that corresponds exactly to the formal semantics, and that again corresponds exactly to the procedure semantics. And that's basically the calculus that you have that runs your code. And in the end, you want to show that all these three elements are the same. So the intended semantics, the formal semantics that you give it, and the procedure semantics of your algorithms. The same, this is now for some code base that we use, some programming code we want to assign values for. And we are going to look into more declarative languages, such as propositional logic or first-order logic. There are plenty of those logics around where you can describe knowledge. So, for example, the knowledge base of a game. And we basically want to do exactly the same. We want to write down our knowledge base in a way that a program can understand it, a compiler or whatever you want to call it. We then want to assign the intended value, the intended semantics, namely, okay, if I say that an adjacent pit has some smell, then this should be somehow be reflected in the mathematical structure that I model. And then I want the algorithm that indeed gives me the right answers whenever they should be given according to the semantics. And that's what we're going to look into in the next hour. So let's have a quarter of an hour break and come back 2-3 minutes past 2:30.